Look closely at this image. Every speck of light, every smear of color is a galaxy. But 1 year ago, we thought we knew the story these galaxies told. We thought we knew the order of the cosmos. Now, all of that has changed. The James Webb Space Telescope, peering back to the very cosmic dawn, has found something impossible. Massive, mature galaxies that should not exist. They are too bright, too old, and too numerous for the universe at that time. The greatest telescope ever built did not just show us the beginning, it broke the beginning. The question is no longer what is out there, but how wrong was our physics?
For decades, the standard model of cosmology, a framework built on the Big Bang and the principles of general relativity, described a logical progression. After the Big Bang, the universe entered a dark age, a period of neutral hydrogen gas that lasted for hundreds of millions of years. Only tiny, seed galaxies were expected to form first. Small, dim clusters that would eventually grow through countless mergers into the magnificent spirals we see today. The venerable Hubble Space Telescope pushed the limits of visible light, catching glimpses of these distant red-shifted precursors. But the epoch of reionization, when the first stars and quasars lit up the darkness and cleared the hydrogen fog, remained shrouded. It was a veil of dust and distance, utterly opaque to visible light. This is where the James Webb Space Telescope, JWST, stepped in. Designed to see in the infrared universe, Webb's massive gold-coated mirror is specifically tuned to catch that light, stretched and reddened over billions of years of cosmic expansion. It was meant to confirm the slow, steady birth of the universe. It delivered a revolution instead. The first deep fields from Webb delivered a visual shock. They were breathtaking, yes, but they were also baffling. The galaxies Webb found, dating back to as little as 300 to 400 million years after the Big Bang, were not the small, irregular toddler galaxies predicted by our lambda CDM cosmological model. Instead, they were bright, massive, and structurally complex. Some already had recognizable shapes like disks or spirals, features that require billions of years of gravitational negotiation and calm merging. The initial findings were so extreme that scientists dubbed these anomalies the universe breakers. Consider the physics. To form a galaxy of, say, 10 billion solar masses in only a few 100 million years, you need immense amounts of baryonic matter to aggregate, and you need it to do so at a near impossible speed. Our models simply do not have enough time for gravity to assemble this much mass this quickly. It challenges the very concept of the universe's structure formation. And the problem doesn't stop with the stars. It extends to the ultimate engines of galaxy growth, black holes. JWST has identified several supermassive black holes in these early galaxies that are far larger than they should be relative to their host galaxy's stellar mass. One example, a so-called greedy supermassive black hole in the distant galaxy Canucks LRD Z8.6, suggests these singularities grew at an almost unconstrained rate. This phenomenon, sometimes referred to as the overmassive black hole problem, suggests that the seeds of black holes were either much larger than we thought, or that the process of accretion in the early universe was far more efficient and explosive than our current physics allows.
The implications of these massive early galaxies force a re-examination of the two great unknowns in cosmology: dark matter and dark energy. In the current paradigm, dark matter provides the gravitational scaffolding for all structure. It clustered first, and ordinary matter fell into these massive, invisible halos to form galaxies. If galaxies formed too quickly, it implies one of two radical possibilities for dark matter. First, perhaps the initial density fluctuations in the very early universe were much larger than the cosmic microwave background suggests, meaning matter was inherently clumpier from the start. Second, and more profoundly, perhaps dark matter itself interacts with normal matter, or even with itself, in ways we have not yet modeled. A different kind of dark matter physics could allow halos to collapse and structure to form at an accelerated pace, enabling the quick birth of giant galaxies. The early universe paradox is essentially a tension in the lambda CDM model. The model is incredibly successful at explaining the large-scale structure of the cosmos, but it is failing at the small-scale, early-time frontier that Webb has opened up. The science community is actively debating the need for non-standard cosmology, introducing new physics to account for Webb's findings. This could involve modifying gravity itself, perhaps through a theory like modified Newtonian dynamics, MOND, or introducing new forms of exotic matter to smooth out or accelerate the growth process. The telescope that was meant to fill in the blanks has instead left us with the most fundamental cosmic question: did we miss an entire crucial chapter in the universe's story?
While the deep field images challenge our origin story, Webb's work on nearby celestial objects is directly impacting our search for life. The telescope is a revolutionary tool for exoplanet atmospheric spectroscopy. By observing the subtle light of a host star passing through a distant world's atmosphere, Webb can identify the chemical fingerprints of life's building blocks. Webb's observations of ultra-hot Jupiters like WASP-18b have given us the first 3D temperature maps of an alien atmosphere, revealing winds, clouds, and complex thermal structures in unprecedented detail. More critically, on potentially habitable worlds, Webb is searching for biosignatures, molecules like water vapor, carbon dioxide, methane, and, crucially, dimethyl sulfide, a molecule strongly associated with biological processes on Earth. The speed and precision of these discoveries bring the concept of extraterrestrial life from philosophical debate to a matter of data analysis.
If massive, complex structures formed quickly in the early universe, it suggests that the conditions for cosmic complexity, for forming the heavy elements necessary for planets and life, were met much sooner than we thought. The implication is a universe that is both older in its complexity and potentially more fertile in its ability to generate life.
The James Webb Space Telescope is, in many ways, a cosmic mirror. It is reflecting an image of reality that is more profound, more ancient, and more contradictory than we had dared to imagine. We sent it out to confirm our theories. Instead, it showed us a universe that refuses to be constrained by our mathematics. Perhaps the greatest discovery is not any single galaxy or black hole, but the realization that our most successful model of the cosmos is, at best, incomplete. We are not at the end of physics, but perhaps the thrilling, terrifying beginning of a new physics. So we must ask, as the final faint light from the cosmic dawn reaches us, demanding an answer, in the face of a universe that seems to defy logic, what new truths about reality must we be willing to accept?